Friends, welcome to Abaqus Acumen. In this video, I will demonstrate how to build Abaqus FE model in Hypermesh. This exercise we will do it for linear static analysis. So Hypermesh is nothing but a preprocessor. Let me show you how the window looks like. So this is a window of Hypermesh version 12, and this Hypermesh tool will be using to build Abaqus linear static analysis FE model. Let me give you first what is the problem definition for it. In the problem, we have simple plate, a simply supported plate with a thickness of 2 mm. Material is steel with this properties, that is modulus and Poisson's ratio. Modulus is 2.1 e raised to 5 MPa and Poisson's ratio is 0.3. And we have this center load, 3-point loads with the 50 Newton magnitude that is acting in negative G direction. So this is a coordinate system. Let's see how to build this in Abaqus. First thing first, we need to see what is the user profile. So this is extremely important to start with the correct user profile. So in your case, could be of any other application, like in this case, this application, that is user profile, is in OptiStruct. So we need to change to Abaqus, and out of that we need to select Abaqus Standard 3D. Okay, this is for implicit linear static analysis. Say just OK. I have jotted down what are the steps need to be performed in Hypermesh to build a FE model, to build a complete FE model. So first step is to mesh this plate geometry with a 2D shell element, and then create a material card, that is material with the steel properties, and then a property collector that is for 2 mm thickness, that is a thickness of the plate, and then the component, that is a component for that plate, and that component having those elements of the plate need to update it with the property collector. So this property collector will go back and assign the material as well. Let's do these 4 steps. So just to save our time, I have already built this 2D shell elements, and now first we have to define material properties. So this is steel. Okay, type is all, card image is Abaqus material. Just create. And for linear static analysis, what essentially we need is elastic properties, that is modulus, so that is 2.1 e raised to 5, and then Poisson's ratio is 0.3. Say return. Now we have to create, say return again, we have to create property collector property. So here we are defining the thickness of the plate. Okay, so say all, and this is a section cell, that is cell section. So that is for, we have only thin sheet, that is 2 mm thick sheet, so it has to be meshed with the cell element. So as we are meshing with the cell elements, using the cell elements, we are taking this section as the cell section. Okay, and then we have to assign the steel for this cell section. Okay, then say create and add it. Thickness is 2 mm, and here so you can put integration point as 3. So as of now I want you to define integration points as 3. So we'll have a separate video wherein we will explain you about for how to define it for our advantage. So as of now, what I want to do is just define 3 and proceed. Now we have to assign this property to the element set, that is plate. So okay, I will just do it again. Go to components, say update, pick the component, select the component, and then select the property, that is, and once you select the property collector, then it will prompt you with the details of this property, that is cell section, material as a steel, and just say update. So you can see the components are updated with this property. With this step, what we have done is we have created this shell elements, we have assigned the material properties, and then we also assigned thickness to these cell elements. Okay, so let's go back and see what are the next steps. So we're done up to the 4 points. So 5th point is apply nodal constraint at 4 corner nodes. Okay, so this is just to represent the simply supported condition. So for that, what you have to do is first we have to create a load collector. So this is a load collector. Say give some name for your convenience. Say here I'm giving BC, that is a boundary condition. You can choose a color of your choice. So I'm going with this color and say no card image, so you don't need any card image. So just say create, and it will set it as a BC as a current load collector. Return. Then go to this analysis page. In analysis page look for constraints. So and it should be on nodes. So we are picking 4 corner nodes, 1 2 3 4. Okay, and then we are applying the translation degree of freedom as a constraint. So what you have to do is we have to have uncheck this rotational degree of freedom, that is d4 d5 d6, and we go with this, check in this DOF1 DOF2 and 3. So what it says is the translation degree, that is DOF1 that is x direction, DOF2 is y direction, DOF3 is in g direction. So these 3 degree of freedom translation we are constraining. Okay, and then load type has to be boundary, and say, so we already selected the nodes, 4 corner nodes, and say create. So you can see these corner nodes are constrained with this DOF 1 2 3. Okay, say return. So let's see what is the next step. Okay, so we have to apply a C load. Okay, that is a force 50 Newton in negative g direction. Okay, we have to go to same analysis. Okay, before that we have to create a another load collector. Let's say force. Okay, so we are using force as a name of the load collector. Pick some another color. So I'm going with the red this time. Keep it as no card image. Say create and go to force. Now you have to select the mid nodes. So these are the mid nodes. So before that, just I want to confirm what are the mid nodes. So there are ways to do it. So you can just say F4 and node between. Okay, so this node that is in between node indicates that this is the line I need to focus and pick. So force 1 2 3. So here I am, magnitude is minus 50, as in it is going to be in a negative g direction. So direction is g. Okay, and here you have to make sure that we have a C load. So this is a C load, is a nothing but a point force load in Abaqus keyword. So say create. Okay, so you can see the C load, that is a point load created in the force load collector. Okay, just say return, and we are done with this step 2. Let's go back and see what is the next step. So we have, okay, so we have to create a node set for 4 corner nodes that we can use it for reaction force request. Okay, so in case if you need to want to know what are the reaction forces at these constraint nodes, so there is a way to request in Abaqus, so that Abaqus will write the reaction force for these constraint nodes. Okay, so how to do it? For that we are going to create an entity set, that is a node set. Let's say we have to have reaction force node set. Okay, and go to nodes, and I am picking these 4 corner nodes which are of our interest. Okay, say create, and if you want to review it, you can review it. Okay, so it will highlight these 4 corner nodes. Okay, it's done. We are ready with the node set, and now we are going to create a output block. So that is output request. When we want to have output requests, for example, we need to have, for this linear static analysis, we have to have displacement, nodal displacement, element stress, and the strains to make a request for Abaqus solver to generate this kind of output for this simulation. So how to do it? This star output request. In analysis page, go to the output block and give some name. So here I am giving output request. So this name could be of your choice. Say create, and once you create it, say edit, and we need to look for output. So this is the output, that is a star output. Okay, and in this we need to select the variable frequency. Okay, so we need to make some changes in this star output keyword. So I will go with the field history field only. Okay, and then variable has to be pre-select. So this is a preferred way of asking, leaving on Abaqus to generate output as per the analysis types. So as we are into linear static analysis, Abaqus, by selecting variable is equal to pre-select, we are requesting Abaqus to generate the default appropriate outputs for this simulation. So this is very important for us. So whenever we do any kind of simulation, it is preferred to have this pre-select option, so that all the basic output will be automatically written into the result file. And frequency, we are giving it 1. So even though it's a linear static analysis, as the simulation is going to do it in one step itself, having a frequency is equal to 1 is sufficient. And now we also are interested in reaction force at those constraint nodes. So how to do it? We have to look for node print. So click on the node print, and here I am going to select a node set, and in node set I am going to look for, we want the summary and also total, and then the reaction force. One can request displacement, reaction force, the point force, so and so forth. But as of now, in this example, we are interested only in the reaction force at the constraint nodes. I am clicking on the reaction force. Okay, and let's summary. Yes, we need a summary, and total. Yes. So there is some limitation in Hypermesh, because Hypermesh is not prompting us to select a node set of this of node set having these 4 corner nodes. So if you remember, we already created the node set. So let me go back and copy that. So there is a way to do it. Okay, so let me go. Okay, so this is the node set name. Just say Control C, that is we're copying it, and then go back to output block, say, and select output request, edit, and here you can simply Control V, that is we're pasting it. That's it. So you can it's kind of a workaround for you. What we have done is, we are through this star node print, we are requesting Abaqus to write a reaction force for this node set. So node set has nothing but these 4 corner nodes, and that is this RF is for reaction force, that is output request, and then this is a star output. Through this we are asking Abaqus to write the nodal displacement, element stress and stress, all these details through this star output keyword. So say return. Okay, we are done with this step, and now we need to create a load step. Okay, so how to do it? You remain on the same page, that is analysis. This is a load step, and say static load step. So we are doing a static linear, let's say. All right, these are the 2 load collectors. So once that is the boundary condition and the force. Okay, so once I pick these two get highlighted on your screen. Okay, say select, and output block, that is we already created, just select it and say create. So once you create it, we also need to edit this. Here through this card, what we are going to select is the static. So this is a static simulation. Analysis procedure has to be static. Choose the static, and then just scroll down. We also need to have data line. So in data line, what we are doing is, we are defining what is the initial increment, say 1.0. So as it's a linear static analysis, no need to worry on the initial increment and the end time period. So we are just giving 1.0, 1.0. You ignore this minimum increment and maximum increment because these are not applicable for the linear static analysis. If you just a quick recap, in a linear static analysis, it solves through the global stiffness matrix method. So it prepares the global stiffness matrix at once and solve through that method. So it is directly solved in one single step. Initial increment will remain 1 and the end period also remain 1. So had it been a case of a nonlinear geometry or nonlinear material, we need to define some very low value of initial increment. Then the load will be slowly ramped up to the end time period of 1.0, so that the nonlinearity in the simulation will be captured. So that is for nonlinearity problem. So here we have only straightforward linear static analysis, just define initial increment 1.0 and end period as 1.0. So we are done with this step 2. Say return, and let me go back. Okay, so low step is done. So the 10th step is export FE model to create ANP file. That's it. So we are all set to export this FE model. Okay, go to export, and in export we have Abaqus Standard 3D. We are selecting a file. Okay, let me have, this is new. Okay, and then so I want to focus on this export option. So in export option, you have to make sure that you are selected all, because if you selected the other two, that is custom and displayed, then the Hypermesh will export the FE attributes, the finite element attributes, which are highlighted on the screen. So what I recommend is that you export and make sure that it is all, so that the all FE attributes, whatever we defined, has to be selected. So it can be done through this export is equal to all, and then say export. Okay, let us go back and see how this input file looks like. Okay, so this is the linear static new, what we have just now exported through the Hypermesh. Let us this is the ASCII format input file, so you can see how the deck file looks like. So this is a star node keyword. Under this we are defining all the nodes, and we have this cell elements, that is elements type is equal to S4. S4 is for, that is the basic type of cell elements, and element set is a plate. So this is the name for this element set, that is this cell element set. And then the thickness we are defining through this cell section. Element set is equal to plate, material is steel. Okay, so this is 2.0 is the thickness, and 3 is the integration point. And then this is a node set, that is the 4 corner nodes, for which we are defining reaction force request, and material is steel with these properties. And then here are some important keywords for linear static analysis. So it has to start with the star step and followed by the star static. Through this keyword we are saying that this is a static linear static analysis, so star static. Okay, and then we are applying boundary condition through this star boundary. So these are the 4 corner nodes, and we are defining 1, 3. So 6, 1, 3, 0.0. What it means is, so 6 is a node ID, so that is one of the corner nodes. Okay, and 1 is a DOI of 1, that is X translation is fixed, and 1, 3. So 1, we have 1, 3, that means the intermediate, that means it is 1, 2, 3 translation degrees of freedom are 0. So 0.0 is that it is restricted. There is no displacement for this node ID 6 in the direction of X, Y, Z. In Abaqus, when we want to constrain the degree of freedom of X, Y, Z, then in that case we have to simply write 1, 3. So once 1, 3 indicates that it is constraining 1, 2 and 3. Okay, so similarly this is written for other nodes, other 3 corner nodes. And then C load is a point force keyword, and the node IDs are these numbers, and it is applied in G direction. the negative g direction, and 50 Newton is the magnitude of the force. And this is the star node, that is we are asking so Abaqus solver to write a reaction force for this node set, that is RF is for reaction force, and then star output is the last keyword by which we are requesting Abaqus solver to write result files such a way that it will include all the essential output parameters like displacement, element stress, element strain. So that's it, we are all set to submit this run through the Abaqus command prompt. So I will show you how to do it. So this is the Abaqus command prompt. You can submit your run through this command prompt. Let me select the directory. CD. Okay, so we have to submit this linear static new INP, that is a job name. So for that you have to write Abaqus j is equal to, that is a job name, int. So once the job is complete, Abaqus will produce the set of files. So you can see the files which are produced by Abaqus in this folder. Essentially we have input file. So this is input file, the one we have created through the Hypermesh, and then these are all these files. Okay, so all these files are created by Abaqus. So out of that I will just tell you about what are the important essential files of our interest. So one is the dat file. This is ASCII file, and this dat file we will find the reaction force data, tabulated data in this dat file. Okay, and this is message file. If you have any errors in the during the simulation, during the analysis, that will be printed in this message files. Okay, this is the ODB file. This is the result file which are going to read it in any of the post processor like Hyperview or Abaqus CAE. So through this you can see the simulation, deform shape, displacement, all those contour maps you can see through this ODB file. And these are the PRT and the sim files. These are, it's not of our use. Okay, so this is something it's created through the solver. And this is the status file, gives a progress of the simulation. And I will just show you the what you find in that file. So let us go and see. Okay, I clicked on the word. You can use instead of word I will use textpad. Textpad is more suitable. Okay, so in textpad let me go. Usually end of this dat file you will see this is the tabulated result. Okay, what it's showing is, okay, so let's go one by one. This is the node ID 1, your reaction force 1, 2, 3, that is in x, y, z direction, and these are the moments in x, y and g direction. So out of that we have this reaction force 37.5 Newton is the reaction force for node 1. Okay, similarly for other 3 nodes we have magnitude. This is the value of reaction force. So as this is a symmetric model with 150 Newton as the total force acting, and this is equally distributed to all 4 corner nodes. So this is how you can just validate that value of reaction force. Okay, and then we will see the ODB file now. So this is the Abaqus CAE window. So once you launch this application, you will get this prompt. So you just say with standard explicit, and then you have to open the ODB file. Let me see. Yes, we have this folder. Okay, so this is the ODB file. Okay, here it is. Say fit. Alright. Okay, and then you have to just see. You can adjust some font over here. So I will do it for you. So it's 14. Okay, alright. So what you can look for is result from field output. So this is the field output, and where we would like to see first displacement. You go to displacement, say magnitude, apply. So you can see is 1.48 as a displacement of this plate. Okay, and then you can also see the stresses, element stresses. For that, go to stress and say 1 misses, say yes. So you can see the 339 as element stresses. Through this video I have demonstrated you how to build a FE model for linear static analysis in Hypermesh, and then how to use this result file, that is ODB file, how to read it in post processor like Hyperview and Abaqus CAE. I hope overall you find this video useful and effective to guide you through the building the model and post processing part for the simple problem. And if you want to have this input file for your reference, you can email us on abacusacumen@gmail.com, and we can send you that input file for your reference. And don't forget to like us on our YouTube channel and Facebook. Thank you. Bye bye.